So it's a privilege to be in this very nice institute, and I really enjoy the workshop. Thank you for the organizer for kind invitation. Just to introduce myself, I'm from Ohio State University. I work on reaction diffusion equation motivated by biology. So my talk today will focus on some result in evolution of dispersal. But I'm also interested in different qualitative properties of solutions. Want to ask PDE question inspired by biology. And so I'm mainly a theorist, but so I have some recent collaboration with people who grow C. elegans. So try to test some theory using a population model in the lab. Right. So the main question I want to discuss today is evolution of dispersal, and I'll frame it as given an environment, I want to study what kind of dispersal behavior is being selected. Okay, so inputs is environmental parameter, and I want to look at selection for dispersal strategy or dispersal pattern. So the stories start with a work of Alan Hastings back in 1983. So where he applied the framework of adaptive dynamics to study the evolution dispersal. I remember I think the title of the paper is Can Spatial Heterogeneity Alone Selects for Dispersal? That was the question. And so to make things clear, I will stick with the two-patch setting, but actually in the original paper, it's already studied in reaction diffusion equation and multi-patch setting. So in the two-patch setting, imagine there are two patches. Okay, and then for a single population, we call the population density in patch I to be UI, right? So the model above is the model for a single population. So imagine the different patch has different carrying capacity K1 and K2, and different growth rate R1 and R2. Okay, so in individual patches, the demographic is given by a logistic growth, and then different patches are coupled by a symmetric diffusion, in this case, with rate D, okay? And so the selection of, so we're interested in selection of this diffusion rate, okay? And to apply the adaptive dynamics point of view, okay, so first the setting is there's a resident species with strategy, small d. It reaches a population equilibrium state. And then we're going to look at the invasion fitness. So if we introduce a rare mutant with a different strategy, but otherwise competitively they are neutral. So that's why the competition coefficient are all 1. So we want to look at ask whether the rare mutants can invade when rare. And the theorem is very clear. So the rare mutant can destabilize the resident equilibrium if and only if it is the slower diffuser, okay? If capital D is smaller than the resident diffusion rates. And the intuitive reason is already given in Hisashi's talk. So naturally, whenever there's a coupled spatial heterogeneity and then two patches are coupled by symmetric diffusion, it introduces a mismatch of resource. And evolutionarily speaking, the source patches are determines the future. So selection acts to minimize the mismatch in the source patches, and it is also related to a broader principle called the reduction principle, coined by Lee Altenberg, and which says that for a linear population model, reducing mixing increases the effective growth rates. One can also ask the selection of diffusion rates in the presence of an environmental drift. Okay, so suppose the two patches are coupled by a drift with rate Q from patch 1 to patch 2, which the species has no control on. So the selection can go to different directions. So supposing the patch capacity are equal, then one can show there's a selection for higher dispersal. So faster diffuser can invade. And in case of unequal patch capacity, one can show there's an intermediate diffusion rate that is selected, or if you have 3 or more patches, then you can show evolutionary branching indeed. So, but I think the commonality is that selection acts to reduce the mismatch of resource. So a perhaps more biological situation, one can also apply adaptive dynamics to study the competition for lights in phytoplankton, but that's another story. Okay, so if we expand to consider the case of conditional dispersal, so diffusion is no longer symmetric, so it can go both ways, and this is D12, this is D21. So dispersal strategy is a function of 2 parameters, Dij. So it turns out that selection goes to a form of balanced dispersal. Okay, so if we require small Dij to be proportional to the ratio of K1 and K2, okay, what it does is that the resulting equilibrium for a single species again can matches the resource perfectly. So this is different from symmetric dispersal. And so if the other species is not balanced dispersal, then it does not invade. Okay, or you can switch the role of UV, okay, which means balanced dispersal invades unbalanced dispersal. Okay. All right. So this indicates selection acts to select for a class of diffusion strategy that is called balanced dispersal. So this is actually connected to a concept introduced by Fredwell and Lucas when they study bird population. It's a verbal framework called the ideal free distribution, where they define IFD to be a state in which no individual can increase its fitness by choosing a different location. Okay, so it has some experiments that shows in some circumstances IFD can be observed. And the connection here, I think it's if you're a person from game theory, okay, so one can think of what happens when a resident species is at a Nash equilibrium. Okay, suppose there's a resident species, it reaches a time-independent state, an equilibrium state, and then when is it a Nash equilibrium? It is when individual is indifferent to choosing any pure strategy. Pure strategy means you're choosing patch 1 or patch 2. So if one identify the net reproduction rates of the environment and then corrected by the broader population, okay, then at Nash equilibrium these two should be equal, okay, and so it leads to equilibration of fitness, and since the population is at equilibrium, there cannot be net growth or net decay. So both fitness has to be 0, and that leads to matching carrying capacity. Okay, so the phenomenon that matching carrying capacity leads to a kind of non-invadable situation is not only proof in 2-patch setting. Okay, so it is proved in various kind of modeling frameworks, and it's pretty robust. Okay, so what happens if we look at time varying environments? So that's one of the point of this talk. So what happens if the environmental parameters and or the diffusion parameters are relaxed to be T-periodic? Okay, so natural things to try is, can we match the carrying capacity, right? So that is seen to be a good strategy, and the answer is a partial yes. Okay, so you can match the carrying capacity if and only if K1 plus K2, the sum is a constant. Okay, and this should be this is an if and only if condition, right? Because if you match carrying capacity, there cannot be net growth or net death of the species, and so the sum has to conserve. Okay, and so this is actually proved by Kensher and Costner in 2018. Okay, so in supposing K1 plus K2 is constant, then IFD or is matching carrying capacity and it is non-invadable. And of course, in general, you don't we don't expect to be able to match carrying capacity. You just think of a one patch situation. Okay, then the population always lags behind the variation in the oscillation in the carrying capacity. All right, so now the next question is what should be ideal free in periodic environments, right? If it is not matching carrying capacity. So one way to think about it is to read Lucas again. Okay, so what is ideal free distribution? So the question is, what is fitness? Okay, how do we define fitness? Okay, so suppose the population is in a time periodic state. Suppose no individual can increase its fitness by relocation. Okay, so fitness is something that is attributed to an individual, not the location. Okay, and the individual now lives in a time periodic environment. Okay, so the individual choice is actually a travel history, right? So throughout the time periodic interval, individual choose either patch 1 or patch 2 at different time. And if it is Nash equilibrium, then the path should be indifferent of gamma. Okay, and this implies that the fitness should be equilibrated across patches, but it doesn't mean they have to be zero for all time. Okay, it just means they are a function of time, but not of space. All right, so this turned out to be a good definition. One can show that suppose a resident species attains the IFD, then it is non-invadable. Okay, by non-IFD species. And the flip side, right? Suppose a resident species is not IFD, then you can introduce a rare mutant with a suitable dispersal strategy to invade, to destabilize it. Okay, so if and only if it is IFD. But one interesting phenomenon is that the ideal free distribution may not be achievable in time periodic domain. Okay, so what we found is that this condition. So our I is the intrinsic growth rate in patch I. So we require our I to be strictly greater than a function m prime over m. Okay, and m is you can consider m as a environmental quantity, but this quantity is defined in terms of Ri and Ki by solving a Bernoulli equation. So this is a unique solution of some Bernoulli equation. Okay, and so the intuition behind this is that given Ri and Ki, the ideal free distribution is given by this expression. And so the requirement Ri bigger than m prime over m is equivalent to saying the environment has no generalized sink. So even though Ki and Ri are positive, there's no like negative growth rates patches, but there can be generalized things. Okay, so do I have 5 minutes? Yeah, thanks. Okay, so for now some summary for ideal free distribution. It is equilibration of fitness among individuals. In static environment, it means matching carrying capacity. In temporal varying environment, it means equilibration of local fitness across space, but not necessarily in time. Okay, so I want to report some recent developments. So we found it. So with postdoc Hua at Shanghai Jiao Tong and with Kensher and Costner, we found a new way to prove theorem. And so we're able to, so previously we studied two species, and this is limited by some mathematical tool. We want to use monotone dynamical system tool, but we found a new way to prove things using a Lyapunov function, okay, which Jishan gave a very nice introduction. And I think there's a connection. So it seems that the existence of ideal-free distribution seems to be connected to the existence of a suitable Lyapunov function. And so with this new tool, we can study the competition of n species, and we can start studying joints ideal-free. So when individual species does not attain ideal-free, but more than one species, maybe species 1 and 2 together, they can form a ideal-free distribution, then they can they can be non-invadable by a third species, and so on and so forth. We also study the joints ideal-free, the evolution stability of joint ideal-free distribution in case there's n prey and n predators. So just to describe the result a little bit. So the setting we study the prey predator is in this setting, in the PD setting. But what the main assumption is this, is that there are n prey species, okay, k equal to 1 to n are the preys, and then k equal to 1 to m are the predators. And what we require in this setting is that, again, there's a symmetry, okay? So we require the fitness among the prey to be symmetric. So neutral competition among the prey and neutral competition among the predators. So under this assumption, one can define ideal-free distribution, okay, or joint ideal-free is when these fitnesses are equilibrated across patches. Okay, so suppose that's the case, then one can show that the particular combination of prey and predator become non-invadable. So selection acts to like hammer the community of species into ideal-free distribution if you allow like repeated invasion by exotic species. And we also, so now we have a sense of what the endpoint of evolution should be in this class of model. And we want to test also the effects of approximate ideal-free. So we introduced a kind of functional. So given the dispersal, we have a way to measure how close we can get to ideal-free. And it turns out, so we did an experiment. We have 2 prey and 2 predator. And there are multiple ways to form a community. So it can be the first prey, first predator, okay, and it can be the first prey and both predators, and so on and so forth. So for each of the combination, one can test how close these combination can get to an ideal-free distribution, can lead to equilibration between the fitnesses of the 2 patches, and it seems to predict the ultimate community that persists if we allow all species to interact. So that's yeah. So we approach it. So it is biology inspired by inspired mathematics, and there are many game theory experts here, and so I would really appreciate any comments and suggestions. So thank you for your attention.
One question.
Okay. Yeah. So I guess in a lot of the, a lot of these, there are a lot of times you and others use sort of PDE models for evolution of dispersal and include sort of advection terms to moving towards better environments and things like this. Has that ever been applied in this patch setting, like studying like kind of direct motion?
Yes. So the advection is motivated by the river models, okay, studied by Mark Lewis and Lucher. They have competition models, and so the evolution question started with PDE, but recently there are more people trying to generalize into patch models. But I would say if the patches are linearly connected, you have a drift. I would say it's expected that the PD result will generalize. So, but what will be really interesting is that there in the patch setting, you have much more richer topology networks, and so the evolution of dispersal in networks will be like I cannot guess what is the the ESS there. So it will be really interesting. So I was hoping to see results arising in that setting. Thank you.